This lesson is about the Bohr model of the atom. The Bohr model is the model that you usually see in clip art, or the one that you might remember from middle school or elementary school when you learned about the different circles around the electrons. After Rutherford's model of the atom, remember Rutherford was the one that discovered the nucleus, so we've explored the Greeks all the way up through Ernest Rutherford. Thomson had discovered the electrons and had the plum pudding model. Rutherford discovered the nucleus, but of course more observations lead to newer models. So let's look at some of those observations. Recently we did a flame test lab, and we also looked at gas discharge tubes through diffraction grating lenses, which has the effect of this picture where we have the hydrogen in the gas tube. It's excited by electricity. We make the light go through a slit to make it into a narrow beam and then split that beam through a prism, and what we see are different bands of color. The diffraction grating lenses that you look through serve the purpose of the slit and the prism. This is some of what you might have seen. We looked at hydrogen, mercury, and neon in their emission spectra, plus in class we looked at a bunch of others. And when you study these, notice that in the upper left-hand corner you can see the Greek letter lambda, which means wavelength. It's being measured in nanometers. So all of these lines have specific colors at certain wavelengths of light. Some things to notice about the spectra, and you can turn back and look at it if you like. The spectra lines have only certain colors for each element. The spectra lines are not a continuous rainbow of color, like when you view white light through a prism. And each element has its own spectrum, like a unique fingerprint. Of course, we wanted to know why. Well, Max Planck was the one who first helped us get a little piece of the puzzle. He was able to determine that the energy of light was directly proportional to its frequency. His formula for his mathematical equation was E equals h nu. That funny looking V there is actually the Greek letter nu, and it stands for frequency. Now the h is Planck's constant. It turns out to be a tiny little number, 10 to the minus 34 for magnitude. So it's a really small number, but it helped us understand how the spectrum lines, or the color of the spectrum lines, was related to their energy. So that was a clue. From that, we recognize that red light, which has a long wavelength and a low frequency, has low energy, and violet light has short wavelength and a high energy. This is in the same order as Roy G. Biv in the visible light spectrum, is in order from lowest to highest energy. We also learned from Max Planck that energy exists in discrete little packets called quanta, and that energy is not continuous. In this example, discrete and continuous are adjectives that mean opposite things. Something that's discrete gets broken down into small little divisible units, and something that's continuous does not. For example, if you wanted to walk up a wheelchair ramp, you can walk up the ramp and stop at any distance above ground level that you wish to stand on. That's because a wheelchair ramp is continuous. If you were to try to stand on stairs, so if you walk up stairs instead of on a wheelchair ramp, the stairs are discrete. You can only stand at certain distances from ground level because you can't stand in between the stairs. You can only stand on the stair steps. So stairs are discrete and wheelchair ramps are continuous. Another example of that would be if you could go to the ATM and get out any matter of money that you want, it would be continuous. But usually when you go to the ATM, you can only get out 10s and 20s, and so it only gives you money in discrete amounts. So we learned that energy comes in discrete packets called quanta. The next scientist to help was Niels Bohr, and he's the one the model is named for. He was able to explain why hydrogen had only 4 spectrum lines and why they were certain colors. His explanation had to do with when atoms absorb or emit energy. Bohr suggested that electrons exist on specific energy levels around the nucleus. And when an atom absorbs energy, the electron jumps to a higher energy level. When the electron falls back down to the lower energy level where it belongs, we sometimes call this the ground state, the atom gives off or emits light energy in the form of a photon, a little bundle of light energy called a photon. You would have experienced this anytime you play with glow-in-the-dark toys, because in order for them to work, like little stars and things you might have on your ceiling, you have to shine the lights on them first and charge them up with energy. And then when you turn the lights off and it's dark in your room, the little toys glow because the electrons are falling back down to the ground state and they give off their energy as that glowing light. Eventually, they stop glowing because they've given away all of their energy. It turns out that the color of light given off in these atomic spectral lines is determined by how far the electron falls. That's a really important part. The color of the light given off depends on how far the electron falls. Here's a diagram to illustrate. You don't have to worry about all the fancy math over here, although you might recognize Planck's constant, E equals h nu there. What we have in the middle, in the very center of the circle, is where the nucleus would be, and these dotted lines represent energy levels. The energy levels are numbered, n equals 1, n equals 2, n equals 3, and so on. So this is energy level 1, here's 2, here's 3, here's 4, here's 5. And notice what the main thing I want you to pick up is that, for example, when an electron falls from energy level 3 to energy level 2, that's why we have this red line right here, because it gives off the amount of energy that would be equivalent to the red color of light. But if it falls from, let's say this is 4 to 2, you get the blue light, and 5 to 2, you get the purple light. Now, some of the falling between energy levels will give off energy in part of the spectrum that we can't see with our eyes, like ultraviolet or infrared light. Our eyes are not able to perceive that, even though that energy exists there. This diagram is a little bit better representation in terms of the spacing. Notice that the energy levels are not evenly spaced. If this was a ladder, it wouldn't be a very good one, because it turns out that the further away you get from the nucleus, the more closely spaced are the energy levels to each other. The nucleus would be down here at the bottom of the picture. So this is energy level 1, energy level 2, energy level 3, and so on. So it depends on if the electron is falling between energy level 2 and energy level 1, you get this yellow line over here. If it falls from 3 back to 1, you get the green line. If it falls from 2 to 1, that's the same as this one. And if it falls from 3 all the way back to 2, this little jump right here, that difference in energy level is apparently not on the visible spectrum for this sample, so we can't see it. The top picture is called an emission spectra because we're looking at the colors of light that are given off. The background is black and we have the two green lines. The one on the bottom is exactly the same, but it's for an absorption spectra. This is when the electron is jumping up to a higher energy level. Notice the amount of energy that it needs to jump from energy level 1 up to energy level 3 is the same amount of energy that it would give off if it came from energy level 3 back to 1. But this is the energy that was absorbed in the green section. So you have a colored rainbow background and black lines. So this one is emission spectra on the top, and the bottom one is absorption spectra, when the light is absorbed. This led Bohr to propose a model something like this. We already knew about the nucleus in the middle. But he said on the first energy level, or some people refer to it as a shell, the first energy level can only hold 2 electrons. The second energy level can hold 8 electrons, and the third energy level can hold up to 18. This is important for you to know because it helps explain a lot of chemistry and chemical reactivity to be able to figure out how many electrons are on the outermost shell or the valence shell of the atom. Now this diagram in particular is kind of generic. It's not for any one specific atom. So some atoms won't use all of these shells. Now you might recall from our study of the periodic table earlier that periods go across, and it turns out that the elements in each period have the same number of shells or energy levels. The elements in the first row, which would be hydrogen and helium, have only one shell or one energy level. Elements in the orange row, the second period, have 2 shells. The third period elements have 3 shells. The fourth period elements have 4 shells. Remember, shell is the same as an energy level. It's a distance from the nucleus, a specific distance away from the nucleus. Groups are the vertical columns on the periodic table, and it turns out that each element in a certain group has the same number of electrons in their outer energy level. The outer shell or outer energy level is referred to as the valence shell, and so the electrons in the outer shell are called valence electrons. Notice that group 1 elements have 1 electron in their outer shell, group 2 have 2 electrons in their outer shell, and so on all the way up to group 8. Group 8 has 8 electrons in their outer shell, except for helium, because remember, helium is in period 1, so it only has 1 shell, and that 1 shell can only hold 2 electrons. So it's kind of the baby of the family. The transition metals have slightly different rules. They're a little more complicated. I'm not going into it during this lesson. Here's a little practice. What you need to do is look at the periodic table. Let's try carbon. If you look up carbon on your periodic table, you'll see it's in period number 2. That means it has 2 energy levels, and it's in group 4, group 4A, so it has 4 valence electrons. Now recall that carbon is atomic number 6, so it has 6 electrons total. So the first 2 go in energy level 1, and the next 4 go in energy level 2. Sodium, energy level 3, so it has 3 shells. It's in group 1, so it has 1 shell. It has 1 valence electron. Did I say 1 shell? It's in the first group, so it has 1 valence electron. What about neon? Find neon on your periodic table. Push pause on the video. See if you can figure out how many shells there are and how many valence electrons, and then push play again when you're ready to go. Neon in the second period has 2 shells. It's in the 8th group, so it has 8 valence electrons. Hydrogen, one shell, 1 valence electron. Sulfur, sulfur is in period 3, so it has 3 shells. It's in group 6A, so it has 6 valence electrons. Potassium, it's in period 4, so it has 4 energy levels. It's in group 1, so it has 1 valence electron. Notice that if you count up all the electrons, it still has 19 total, because its atomic number is 19. So 2 on the first level, plus 8 on the blue level, that's 10, plus 8 on the green level, that's 18, plus the 1 orange one, that makes 19. Now helium's tricky because helium has 1 shell and it's in the 8th group, but remember it doesn't have 8 electrons, it only has 1 shell, so it can only have 2. What helium has in common with all the other elements below it, the noble gases, is that their valence shell is full. Time for a little practice with the Bohr model.